In section 4.3, what we're going to do is put together what we learned in previous sections to graph functions. There are some guidelines when you graph functions, and these guidelines are in your e-text. First, if you're not given an interval to graph, find the domain. That will tell you how large your graph needs to be. Number 2 is to locate symmetry. Now, I actually don't do this. The textbook likes you to look at symmetry second, but I rarely look at symmetry. So if you don't remember, we have even and odd functions. An even function says if we replace x with negative x, the y value remains unchanged. That would be symmetry about the y-axis. In an odd function, you can take the x out from inside the argument and put it in the front of the function. That symmetry would be symmetry about the origin. Again, I rarely use this. Number 3 is to find the first and second derivatives. Okay, so remember that's going to give us, with the first derivative, possible local mins and max, increasing, decreasing. Second derivative can give us inflection points and concavity. So once we find the first and second derivatives, we're going to find critical points for the first derivative and possible inflection points from the second derivative. So those critical points would be where we test to see if we have intervals of increasing and decreasing. And we will also identify our extreme values, local and absolute extrema, and inflection points. If that's not enough, you can always look at asymptotes and intercepts. And then the last thing you would do is choose an appropriate window to graph. Let's go ahead and apply these in example 1. If I look at this function f, it's a polynomial. Now, no interval is given for me to sketch my graph, so I have to look at the domain. And the domain of a polynomial, so the domain of this function f, it's going to be all real numbers from negative to positive infinity, right? There's no place where this function is undefined. The next thing I'm going to do is I'm not going to look at symmetry. I'm going to go straight to computing my first derivative. So the first derivative is going to be 3x squared minus 4x plus 1. Okay, so let's go ahead and find critical points. I'm going to set my derivative equal to 0. And what's nice about this first derivative is it's actually factorable into 3x minus 1, x minus 1. So if I set each of these factors equal to 0, I'm going to have x is equal to 1/3 and x is equal to 1. So these are going to be my critical points. So the next thing I'm going to do is I'm going to find my second derivative. The second derivative of this function is going to be 6x minus 4. So when we set the second derivative equal to 0, what we'll be finding is possible inflection points. So solving, I get x is equal to 2/3. And this would be my possible inflection. What I'm going to do now is I'm going to make a chart that's going to contain both my first and second derivative. I'm going to come back up here and I'm going to make a number line Since my domain is from negative to positive infinity, my number line will go from negative to positive infinity. I'm going to list all my critical points and possible inflection points on my graph from small to large. So we'll have 1/3, 2/3, and 1. Okay, so I'm going to put the first derivative and the second derivative on the same chart, and you'll see why in just a little bit. I need some test points. Maybe from negative infinity to 1/3 I should look at 0. From 1/3 to 2/3, maybe 1/2 is between both of those. 2/3 to 1/3, and then from 1 to positive infinity I'll just put in 2. So my first derivative, if I put in 0, my first derivative will be positive, but my second derivative will be negative. And I'm just going to go ahead and separate these. At all my critical points. If I put 1/2 into my first derivative, it's negative. If I put it into the second derivative, that's also negative. If I put my test point 3/4 into my first derivative, it's going to be negative. And then my second derivative would be positive. If I put in 2, the first derivative and the second derivative are both positive. So let's look at what that means. From negative infinity to 1/3, my first derivative is positive, which means my function is increasing. Excuse me. But my second derivative is negative, which means it's concave down. So it's going to look like this. Okay? Increasing, concave down. Now from 1/3 to 2/3, they're both negative. So I have decreasing, concave down. From 2/3 to 1, I have a decreasing function, but it's concave up. And then from 1 to positive infinity, increasing, concave up. So that's what the shapes would be. Now what's really nice here is at 1/3 my first derivative changes from positive to negative. So that tells me that there's a local max here at 1/3. And at 3/4, or 2/3, sorry, my second derivative changes sign from negative to positive. So that would be an inflection point. At 1, my first derivative changes from negative to positive. So that would be a local min. So my first and second derivative told me a lot about this function. And in fact, it basically showed me what the graph is going to look like. I can just sketch it as looking something like this. So that's the basic shape of the graph, where I have a local max, a local min, and an inflection point. The problem is that I need some points so I can figure out where to put this graph on my coordinate system. So let me go ahead and draw a grid. And I'm not going to have too much on the negative x-axis because most of these critical values are positive values. So let's look at 1/3. This will probably not be to scale either. 2/3 and 1. Okay, so where do I put my graph? Well, a nice point that we could try for is maybe a y-intercept. So this is where we're going to be looking at those additional steps in the guidelines. Okay. There are no asymptotes. So y-intercept, if x is 0 in my original function, then y is -5. So I'm just going to pretend like this is -5. Again, this is not to scale. So I have this point. Great. So I know what's going to happen is the function is going to go up, and there's going to be a local max at 1/3. Now what that actual value is, I don't know. I just know I have a local max at 1/3. So I'm going to have to put this into my function to figure out what that value is. Now we're supposed to be pretending that we don't have a calculator, that we're doing all of this by hand, and it's really awful. It turns into 131, I believe, over 27, but you guys can double check me on that. So when you do the long division, that's approximately -4.85, and I'll stop there because the decimal just keeps going for a pretty long time. Okay, so that's at 1/3, it's just a little bit higher, right, than the -5. So I'm seeing that the graph is going to go up because that's what my chart says. And then it's going to come back down, and at 2/3 there's going to be an inflection point. So let's go ahead and figure out what the value of the function at 2/3 is, so I can see where my inflection point is. Again, this is pretty horrible. I got -133 over 27. And that's going to be approximately -4.93. So it's not going to come down too much. So again, we're looking at concave down, but a very, very slight curve. Then we get an inflection point at 2/3, and it's going to be concave up. So let me go ahead and find some more points. Let's look at what f of 1 is. And thank goodness, that one's easy. That's going to be -5. So at 1, we're going to come down again at 5, should be about here, -5, sorry. And we're going to change the concavity from concave down to concave up. And then it's going to remain concave up, so the graph is just going to keep going. Okay. And then this would remain concave down. So this is the basic shape of my graph. Now it's just a sketch, but I should label some points. So I'm going to label the y-intercept 0, -5, and maybe I'll label all of these points that corresponded to some critical points. So 1/3 -4.85, 2/3 -4.93, and it's okay to use the approximation here. And this point here would be 1 -5. So that would be using the first and second derivative to sketch a graph. Do 2 more examples here. In example 2, we want to sketch the graph of this rational function. Now this one's going to give me a lot of headache, because technically if I am going to use the first and second derivative, I have to use the quotient rule twice for both the first and the second derivative. Again, I don't have an interval to graph on, so I need to first figure out what the domain of this function is. Since it's a rational function, the only problem I'm going to have is when the denominator is equal to 0, which occurs when x is equal to positive and -3. So the domain of this function is going to go from negative infinity to negative 3, union, negative 3 to positive 3, union, 3 to infinity. So notice that this domain is broken up into 3 pieces. And that tells me a lot. It tells me that I'm going to have 3 pieces to my graph. I'm avoiding taking the first and second derivative because I'm avoiding using quotient rule. So I think I'm going to find some nice points, like maybe a y-intercept. If I put in 0 for x, I get 0 back for y. Maybe I'll look at the x-intercept. If I set this function equal to 0, I end up with x is equal to 0. So I have an x and a y-intercept. Also notice that if I set the denominator equal to 0, which I did to find the domain, that also gives me vertical asymptotes of x equal to 3 and x equal to negative 3. I also know that since the degree on the top is 1 and the degree on the bottom is 2, that I have a horizontal asymptote of y equal to 0, again because the degree on the top is smaller than the degree on the bottom. So I have a lot of information here. Now I'm going to have to find the first and second derivative. Okay, so my first derivative by using the quotient rule would be x squared minus 9 times the derivative of the top, which is just 1, minus x times 2x, all over x squared minus 9 squared. So if I were to clean up the numerator, I would have x squared minus 2x squared, which would be a negative x squared minus 9 over x squared minus 9 squared. Okay, so critical points for the first derivative are where it's undefined or where it's equal to 0. So the first derivative is undefined when that denominator is equal to 0, which would be at x equal to plus or minus 3. Now, where it's equal to 0 is where the numerator is equal to 0. But negative x squared minus 9 is never going to be equal to 0 because the x is squared. So that's always going to be equal to some negative number. Again, it's never going to be equal to 0. So plus minus 3 are my only critical points. The problem is that's not in my domain. But I'll keep those there because those are where my vertical asymptotes are. Let's look at the second derivative. Oh, this is going to be fun. Okay, so x squared minus 9 squared, derivative of the top would be a negative 2x. We're going to subtract the top. Derivative of the bottom involves the chain rule, so to keep the x squared minus 9 times the derivative of x squared minus 9, which is 2x. That was fun. All right, so this is going to be all over x squared minus 9 to the 4th power. Okay, so what I do notice is that in the two terms on the top, I can factor out x squared minus 9 and cancel it with the denominator. So I do notice that this is going to be equal to x squared minus 9 times negative 2x. And this minus negative x squared minus 9 can change into a plus. X squared plus 9 times 2. The x squared minus 9 cancels. I have a 2x. And then now I have x squared minus 9 to the 3rd power. And if I continue to simplify this, in the numerator I can end up factoring out a 2x. And then what remains in the parentheses, if I clean it up, would be x squared plus 27. All over x squared minus 9 to the third power. Well, that was fun. So I need to find possible inflection points. I'm going to be looking at where the second derivative is 0. So that would be where the numerator is 0. And x squared plus 27, notice that the numerator is already factored. So if I set each of those factors equal to 0, the x squared plus 27 will never be equal to 0. But the 2x is equal to 0 when x is equal to 0. So that's going to be a possible inflection. All right. So I'm going to put the first derivative, first derivative and second derivative on my graph, as I did before. Now, -3 and +3 aren't technically critical points because they're not part of the domain, but I'm going to put them on my graph because they are asymptotes, vertical asymptotes. So I want to see how my graph is going to behave on either side of my vertical asymptotes. So I'm going to put in -3, the possible inflection point of 0, and +3. And I'm going to look at my first derivative and my second derivative. Some test points for infinity to -3, maybe a -4. Oh, these are nice points. -3 to 0, maybe -1. 0 to 3, I could use 1 as a test point. And from 3 to positive infinity, I'll use 4. So what I'm going to do is I'm just going to do the first derivative all the way across. If I put in -4 into the first derivative, it's going to be negative. If I put in -1, I believe that's also negative. At 1, it's negative, and at 4, it's negative. Okay? And then at -3 and +3, I have these vertical asymptotes, and at 0, I have a possible inflection. If I put in the test points into the second derivative, I'll end up with a negative, positive, negative, positive. So let's think about this and see what it looks like. Well, from -infinity to -3, it's going to be decreasing concave down. From -3 to 0, it's going to be decreasing concave up. And then from 0 to 3, we're going to have decreasing concave down. And from 3 to infinity, it's going to be decreasing concave up. All right, let's put this all together with a graph. I know I have vertical asymptotes at -3 and 3, so I'm going to go ahead and just sketch those in. And I'll go ahead and label these as well. X is equal to -3. And then I have x is equal to 3 would be my other vertical asymptote. Probably should draw a 3 in here. Some points that I do know that I have x and y intercept at 0, 0. All right, so I'm done. I can sketch my graph. Notice that between -3 and 0, it's going to go, and now remember my graph has to follow the asymptotes. So it's going to be decreasing concave up. So I have no choice. I have to draw the graph to look like this. And then we have an inflection point at 0. It's going to be decreasing concave down. And the graph has to follow the asymptotes. And I just have one point here, the x and y intercept. Okay, let's sketch the portion of the graph from 3 to positive infinity. Well, it's going to be negative concave up, and it has to follow the asymptote. So it has no choice. It has to do this. Now, how do I know it follows that x-axis? Well, recall that we also have a horizontal asymptote that my graph has to follow of y equal to 0. So let's look at the left of negative 3. Well, my chart says it's decreasing concave down. So I have no choice. Since it has to follow the asymptote, the sketch will look like this. Now you can get a more accurate sketch by finding more points, but honestly this is just a sketch. And besides the pain of taking the first and second derivative of a rational function and using quotient rule, it actually turned out pretty nice. So let's do our last example. In this last example, example 3, I actually have an interval to sketch the graph on. The interval is from 1 to 9. So I don't need to find the domain for my function. So let's go ahead and find the first derivative. Our first derivative is going to be 1/2 x to the negative 1/2 plus 3 halves x to the negative 3 halves. Okay, so what I'm going to do is I'm going to find my critical points by setting the first derivative equal to 0. And you know what, I can see that I could factor out an x to the negative 3 halves. What I have left over when I factor that out would be a 1/2 x plus 1. Let me rewrite this into 1/2 x plus 1 in the numerator, and I'll go ahead and make the negative 3 halves exponent positive by dropping that into the denominator. So for me it's easier to see where this derivative is undefined. That would be when x is 0, and where it's 0, that would be when x is negative 2. So if x is equal to negative 2, then my first derivative is 0. And if x is equal to 0, then my first derivative is undefined. So those are my possible critical points. However, these points are not in the interval from 1 to 9. So they're of no interest to me. Let's look at the second derivative. When I compute the second derivative, it looks like it's going to be negative 1/4 x to the negative 3 halves minus 9/4 x to the negative 5 halves. So again, I want to find possible inflection points by setting my second derivative equal to 0. And I can see that I can factor out an x to the negative 5 halves. I could probably take out a negative 1/4 as well, but I think I'm just going to stick with x to the negative 5 halves. what's left over will be a negative 1/4 x minus 9/4. I'm going to do what I did before. I'm going to drop the x to the negative 5/2 into the denominator. So I have negative 1/4 x minus 9/4. All of this is over x to the positive 5/2. So now it's easier for me to see that the only way this numerator is going to equal 0 is if x is equal to a negative 9. Then I'll have a positive 9/4 minus 9/4, I'll get 0. However, negative 9 is not in the interval that I'm interested in, right? So I don't really have any critical points there. Let's go ahead and look at our number line from 1 to 9. So this is the interval that I'm interested in. Notice that there are no critical points for the first or second derivative. That means I only have to look at whether the first derivative is negative or positive and the second derivative is negative positive in this interval. I think I'll use the test point. Why not 4? That's halfway between 1 and 9. So if I put 4 into my first derivative, it looks like it's going to be a positive over a positive. So it's going to be positive. And I'm looking at where I have written it as a fraction. So if I look at my second derivative and I put in a positive 4, I'm going to have a negative over a positive. So my second derivative will be negative. Okay, so on the interval from 1 to 9, my function is going to be increasing concave down. Okay, so increasing concave down. It's going to look like this. But where do I graph it? I need some points. So we're going to look at 1 and 9. And I have no critical points to put in. I don't know if there's definitely any y-intercepts because I'm not even going to be graphing on the y-axis. So I could have a possible x-intercept, which means I'm going to have to set my function equal to 0 and solve for x. Kind of don't want to do that just yet. So instead, what I'm going to do is I'm actually going to put in 1 and 9 into my function. So my original function, if we go back up to the top, is x to the 1/2 minus 3x to the negative 1/2. So I think it might be easier if I write this as the square root of x minus 3 over the square root of x. Okay, so if we put in 1 for x, I have 1 minus 3. That would be a negative 2. So it's going to pass through the point 1, negative 2. And if I put in 9 for x, it's going to be 3 minus 1. So that's going to give me a positive 2. My graph will pass through the point 1, negative 2 and 9, 2. So why don't I just pretend that this is negative 2 and positive 2. So 1, negative 2, 9, 2. And my graph is going to be increasing concave up. So let's go ahead and put in some points. All right, so that's it for this section.